Hi there. In this video we're going to take a little bit more abstract approach to the derivative. In the previous two videos we looked at a more concrete perspective and we looked at the derivative in terms of instantaneous velocity. We're going to basically extend that to a more general idea of a derivative. So here we go. If you consider this curve x squared and we're interested in the derivative of x squared, well, first of all, what do I mean by that? Well, the last two videos would show you that all a derivative is a rate of change. It's an instantaneous rate of change. If I said, what is the derivative of x squared at 1, then I'm looking for, here's 1 right here, then I'm looking for the instantaneous rate of change, which is really just slope. A rate of change is just slope, or slope is just a rate of change. I'm looking for the slope of that function, x squared, at 1. Well, it turns out the slope of this tangent line is right around 2. Okay, so we would say that the derivative of x squared at 1 is equal to 2. Now it's not 2.02. You have to understand that there's some rounding error that's occurring here in this sketch. Okay, what about the derivative at let's see if we can do the derivative at 3. So we'll put both dots at 3. And we can read off the slope off to the side here is 5.98. And again, if you're lost on where these numbers come from, I developed these fairly extensively in the last couple of videos. Okay, so really, all a derivative is an instantaneous rate of change. It's the slope of a tangent line to a curve at a given point. Okay, right now, this rise and this run represents the slope of a secant line. Okay, this rise right here I've labeled as f of x plus h minus f of x. Well, where did that come from? F of x plus h is simply the height of this green ball. That should make sense because this yellow ball is x plus h. Therefore, the height is f of x plus h. Well, the height of this red ball is simply f of x. So if I subtract the height of the green ball from the height of the red ball, I get this distance right here. Okay, and also, if I define this distance to be h, and if this is x, then it makes sense that this yellow ball is x plus h, giving us a distance of h. So really, any slope of this line, no matter where this line exists, the slope of this line is simply going to be the rise, which is this guy, divided by this guy. Okay, and more importantly, if we let h run to 0, then this line becomes a tangent line. But I want you to note that all of these values still remain, they still take on the same meaning. Okay, we still have f of x plus h minus f of x, and this is really h right here. Okay, so let's just go ahead and let's calculate the derivative of this curve at 2. Let's see what our curve says. Okay, it's estimating it to be right around 4. Okay, so how did it get that? Well, we're calculating the derivative at a very specific value for x. We're going to let x equal 2 in this case. So 2 would be x, and then this guy right here would be 2 plus h. All right, well, how would we actually solve this analytically? Well, it comes down to the question, what is the derivative of this function? And before I answer that, I want to answer the more specific question of what is the derivative when x is 2. So the derivative when x is 2 is going to be the following. We want to evaluate the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Okay, and if you watch the video, the idea of a skeleton equation should make sense to you. And again, if you hadn't watched it, all I mean by that is wherever I see my variable from my original function, I replace it with some parentheses. So here's my original function, my input squared, and I simply plug into my parentheses whatever's in here. So this is 2 plus h. So this right here is really this guy. That is f of 2 plus h right there. Okay, minus what? Well, we're going to minus f of 2. Well, what is f of 2? That's going to just be 4. 2 squared is just 4. All over h. Okay, now, continuing on, I'm going to expand this, and I get the limit as h goes to 0 of 4 plus 4h plus h squared minus 4. Okay? And the numerator, the denominator, I just get h. Well, looking very carefully, I can see that this 4 and this negative 4 go away. And I get, up top, I get 4h plus h squared. Now the last thing it looks like can happen is this h here can reduce with an h in the numerator. So my final limit statement before I actually evaluate it is going to be 4 plus h. Okay, now this looks like a pretty straightforward limit, and if I want to evaluate it, I just substitute 0 in for h to get 4. Well, what does that 4 mean? Okay, the 4 is the slope of the tangent line to this curve when x is equal to 2. We already saw that. Well, what if I didn't know? What if I didn't know what x actually equaled? What if I just want to know a general formula that would help me calculate, so I didn't have to do this difference quotient over and over and over again? What if I wanted a formula that would just spit out the slope every single time? Okay, and that amounts to evaluating the same difference quotient, except instead of letting x equal to 2, we're just going to evaluate this general difference quotient right here. Okay, so basically we're going to repeat the process. I'll do this hopefully fairly quickly. But again, instead of x equaling 2, we're just going to leave our x in there. So what is f of x plus h? Well, f of x plus h is simply going to be x plus h squared minus f of x. And what is f of x? F of x is simply x squared. Okay, and this is all over h. Okay, going through the algebra. The algebra is exactly the same, so I'll try to do this quickly. This should be x squared plus 2xh plus h squared minus x squared all over h. And you'll notice that your x squareds drop out. At the same time, you're going to get these h's that cancel, so I'll combine steps here. It's the same as the problem up above. So again, my x squareds cancel. I have an h that cancels, and I'm left with 2x plus h. Okay, now if I evaluate this limit now, I'm letting h go to 0. A common mistake is to maybe put this 0 in for this x. Remember what we're letting go to 0. We're letting h go to 0. So we substitute 0 in for h, and I'm left over with 2x. Well, what does 2x represent? 2x represents the derivative of f of x. Okay, so we could write f prime of x equals 2x. The prime just denotes that we're talking about the derivative of our original function f. Okay, so what exactly does this tell us? Well, it tells us the slope of any tangent line to this curve at any given point. Let's see if it actually works. Let's go ahead and let's go to 1 here. And let's let h go to 0. We're letting h go to 0 here. And notice what the slope of your tangent line is. Okay, the slope looks like it's getting really close to 2 here. Okay, well, what is my x value? My x value is 1. So back here, if I wanted to know what is the slope of f at 1, I could simply evaluate f prime of 1. What does this mean? This means that the slope of the tangent line to f at 1 is 2. That's my instantaneous rate of change. Let's do one more to see if it really works. I know it does. I'm just doing it for kicks, I guess. Let's go to 3. Okay, if I go to 3, we're at 3 right here, and now we let h go to 0. We're letting h go to 0. Our secant line is becoming a tangent line, and the slope of that thing looks like it's right around 6. In other words, when x is 3, it looks like the slope of my tangent line is 6. Okay, so again, if I evaluated it with my new formula, I could evaluate f prime of 3 equals, well, what is it? 2 times 3 is 6. And 6 represents the slope of the tangent line to the curve x squared at the point 3. So that's a derivative in a more abstract sense. I hope that made sense. Look for more examples to come. See you later.